Welcome to the Deep Dive. This is where we take a topic you're curious about, look at the sources you've shared, and, well, we boil it all down for you. It's your shortcut to getting informed.
That's the idea. And today we're diving into something pretty fundamental, roads. Specifically, how agencies figure out which ones need fixing.
Right. You, our listener, pointed us towards a really interesting study for the South Carolina Department of Transportation, SCDOT. They've been looking into a tech called the Traffic Speed Deflectometer, or TSD.
Yeah, TSD. It's about pavement management. How do we know if a road is really okay underneath the surface?
So our mission today is to unpack this TSD tech. How does it work? Why was SCDOT interested? And, what does this study actually mean for the roads you drive on?
We want to understand the findings and what they could mean for future road work, basically giving you the inside scoop.
Exactly, and we've got our expert here to help us navigate the technical side and the bigger implications. Okay, let's jump in. How does South Carolina currently pick its road projects? What's the process?
Okay, so SCDOT uses a points system. It's all laid out in their engineering directives, number 63 to 65. They score roads based on several factors.
A point system. All right, what kind of factors are we talking about? What gets the most points?
Well, the biggest one is the Pavement Quality Index, PQI. That's 40% of the score.
40%. Okay, what else?
Then you've got the International Roughness Index, IRI, that's 15%. Average daily traffic, also 15%.
So how rough the ride is and how busy the road is.
Yeah.
Makes sense.
Exactly. Then smaller chunks, percent patching is 5%. Average daily truck traffic is another 5%.
Oh, trucks are important.
Definitely. Then there's whether it's on the state freight network, strategic corridor network, its functional classification, those are each 5%. And finally, state safety programs, another 5%.
Wow, okay. That's a lot of things to track, so they add all that up.
That's the first cut, yeah. That gives them a prioritized list. But then the district engineers take over.
They go out and look at the roads.
Right. They do a field review using some secondary criteria worth up to 400 points. Things like relative condition, how it connects to other roads, if it makes sense to do it as part of a bigger project, that sort of thing.
Okay, so it's a mix of data and on-the-ground assessment. But that PQI number, the 40% one, that sounds really dominant in the initial scoring. What does it actually measure?
It's key, yeah. But the report points out something important. PQI is mostly about the surface, how smooth the ride is, visible cracks, that kind of stuff.
I see where this is going. So a road could feel okay, get a good PQI score.
Exactly. But underneath, it could have structural problems brewing.
Like hidden damage.
Precisely. And the study mentions earlier research, going back quite a way, that found PQI often doesn't correlate well with the actual structural health. A road might seem fine now, but be structurally weak and, fail much sooner than you'd expect based on the surface.
That makes total sense. It's like judging a book by its cover, but for roads. Okay, so if PQI isn't the whole story, how do we see underneath? That's where this TSD comes in.
That's the idea. The Traffic Speed Deflectometer. It's pretty neat technology.
Tell me about it. What is it?
Imagine a truck, basically, driving at normal highway speeds. It has lasers, Doppler lasers, measuring how much the pavement bends or deflects under its weight as it rolls along.
Wow, at traffic speed, so no closing lanes down.
Exactly. That's a huge advantage over older methods like the falling weight deflectometer, the FWD.
FWD, right. I've seen those crews out there stop in traffic.
Yeah, FWD requires stopping, testing a spot, moving, stopping again. It's slow, costly, and obviously disruptive. TSD gives you continuous data the whole length of the road without the closures.
Continuous data. That sounds much more comprehensive. So SCDOT got hold of some of this TSD data.
They did. Back in 2019, they were part of these pooled fund studies. Think of it like states chipping in together to test new tech.
Okay.
Without that, they collected about 950 miles of TSD data across 8 major routes in South Carolina.
950 miles. That's a serious amount of data. What kind of truck does this, and what exactly is it measuring?
The specific vehicle used was called an IPAVE Intelligent Pavement Assessment Vehicle. It's like a semi-truck setup, and it has sensors measuring the speed of deflection at different distances from the wheel load.
Speed of deflection, not just how much it bends.
Right. It measures the velocity profile of the deflection bowl. The sensors are placed at specific offsets, 110 millimeters, 210, 310, and further out up to about 1.5 meters. From those velocity measurements, they calculate the actual deflection amounts.
Okay, so measuring the bend at different spots tells you more about the structure.
It gives you a much better picture of how the load is distributed through the pavement layers, yeah? It's not just how much it sags right under the tire, but how the whole structure responds.
Got it. So how does that bending data translate into a measure of structural health? You mentioned an index.
Yes, the Structural Condition Index, or SCI. This study focused on one specific version, SCI 12, which is equivalent to SCI 300 in metric units.
SCI 12. How's that calculated?
It's basically the difference between the maximum deflection right under the load, which they call D0, and the deflection measured about 12 inches or 300 millimeters away, D300. That difference tells you something about the structural integrity.
Okay, D0 minus D300 gives you SCI 12, a measure of structural condition. So they crunched the numbers for those 950 miles. What did they find? Did it confirm the suspicion about PQI?
It absolutely did. They took the TSD data, the SCI 12 values, and compared them directly with SCDOT's existing PQI data for the same road segments.
And the results? Drum roll.
Well, the big finding was a pretty low correlation between SCI 12 and PQI for 50% of the routes they studied.
Half? What?
Yeah, about 28% showed moderate correlation, and only about 22% showed a high correlation.
So for a lot of the roads, how good it looked on top had little to do with how strong it was underneath.
That's the key takeaway. It really confirms that PQI alone doesn't capture the true structural condition, which impacts, how long the road will actually last and how it might deteriorate.
That's huge. How do they actually match up the data? The TSD measures tiny segments, right? And PQI is longer.
Good question. The TSD collects data in very short 0.01 mile segments. SCDOT's PQI data is in 0.1 mile segments. They use GPS coordinates and a Python program to link them.
Computers to the rescue.
Basically, yeah. They aggregated the short TSD segments that fell within the boundaries of each longer PQI segment to get comparable data.
Makes sense. So now they have matched structural data, SCI 12, and surface data, PQI. How do they decide what counts as good, fair, or poor structure based on SCI 12?
They developed thresholds for SCI 12. Based on their analysis and aiming to align with other goals, they set good as less than 1.6.
Okay, low SCI 12 is good.
Right. Fair was defined as between 1.6 and 3.3, and poor structural condition was anything above 3.3.
And why those specific numbers, 1.6 and 3.3?
They linked these thresholds to SCDOT's targets in their Transportation Asset Management Plan, the TAMP. That's their long-term plan for keeping roads in shape, often tied to federal performance measures. So it makes the TSD data directly relevant to their existing goals.
Clever. Okay, so now we can categorize roads by both surface, PQI, and structure, SCI 12. The study talks about areas of interest. What are those?
Right. So imagine a grid. Good, fair, poor PQI on one side, good, fair, poor SCI 12 on the other. That gives you 9 boxes, 9 possible combinations of condition.
9 possibilities.
The areas of interest are the boxes where the TSD structural data tells you something really important that PQI alone might miss. They highlighted 3 key areas.
Okay, what's the first one?
Area 3, that's roads with good PQI. They look and feel fine, but poor SCI 12.
The hidden problem roads.
Exactly.
Right.
If you only look at PQI, you might think these roads are fine, maybe just need minor upkeep. But the TSD shows they're structurally weak. Applying the wrong treatment here, like just a thin overlay, could be a waste because it won't fix the underlying issue.
Right, throwing good money after bad. What's the next area?
Area 2, fair PQI and poor SCI 12. These roads are maybe borderline based on the surface condition. They might not be top priority if you only use PQI.
Structurally.
But structurally, they're in bad shape according to the TSD. These are roads at high risk of falling apart faster than expected. The TSD data flags them for maybe more urgent attention or a different type of repair than the fair PQI might suggest.
Okay, so flagging roads that might otherwise slip through the cracks. And the third one?
Area 7, poor PQI but good SCI 12. These roads look bad, feel rough. Based on PQI alone, they might be candidates for expensive reconstruction.
Tear it all up and start again.
Right. But the TSD data shows the underlying structure is actually sound, so maybe all it needs is a less drastic, cheaper preservation treatment focused on the surface issues.
That sounds like a huge potential for savings. Did they find many roads falling into these areas of interest?
They did, yeah. The report breaks it down route by route. For example, SC9 had about 19% of its length in these areas, US 321 had 26%, US 378 had 23%.
So a significant chunk of these major roads.
Definitely. And some routes showed interesting patterns, like US 17. It actually had the best overall structural condition, SCI 12, but the worst functional condition, PQI.
A classic Area 7 example. Looks terrible, but solid underneath.
Exactly. Perfect candidate potentially for saving money with a smarter repair.
This really highlights the value of having both pieces of information.
Yeah.
So how did the study suggest SCDOT could actually use this TSD data day to day?
They developed a tool to make it practical, the TSD score. It's designed to help those district engineers factor structural condition into their decisions.
A TSD score. Okay. How does that work? Is it complicated?
No, it's pretty straightforward, actually. You look at a potential project section, you figure out the length within that project that has poor structural condition based on the TSD data.
All right.
The score is that length of poor structure, the total project length, times the percentage of pavement with poor structure, then times 100.
Length divided by total length times the percentage times 100.
Yeah, so basically a higher score means more of the project length is structurally poor, or the proportion of poor structure is higher, or both. It gives a single number from 0 to 100.
And higher score means?
Higher score means worse overall structural condition for that project segment. 0 would be great structure, 100 would be uniformly poor.
Got it. Can you walk through a quick example?
Sure. Say you have a 10-mile project. The TSD finds 3 miles have poor structure. That's 30% of the length. So the score would be 3 miles, 10 miles. That's 0.3 times 30%, which is also 0.3 if you write it as a decimal. But they use the percentage number 30 here. I think the formula might be slightly different in practice. Let me recheck the source. Yes. The formula is length poor, total length, poor percent, poor 100. So 310, 3100. Wait, that gives 900. That can't be right. Let's reread that formula calculation description carefully. Okay, apologies. Let me recalculate based on the description. Length of pavement with poor structural condition, total project length. Percentage of pavement with poor structural condition, 100. Let's try that again. 3 miles, 10 miles is 0.3, or 30%. The percentage is 30%. So maybe it's just length fraction percent value. So 0.330 equals 9. Okay, that makes more sense. A score of 9.
A score of 9. Okay. So if, say, 5 miles were poor structure out of 10.
Right, that's 50% length. So 5,
Yeah.
10, 50, well, 0.550 equals 25.
Yeah.
A higher score, reflecting the worst condition.
Okay, that makes sense now. A simple score to quickly gauge structural issues. How would engineers see this score?
The researchers built an Excel tool called the secondary filter. The idea is headquarters staff would run the TSD data through this tool. It calculates the TSD score for each potential project on their list.
And adds it to the spreadsheet.
Exactly. It adds a new column with the TSD score right alongside the PQI and other info they already send to the district engineers for their field reviews.
So it slots right into their existing workflow, giving them that extra structural insight when they're out looking at the road.
Precisely. It's not meant to replace their judgment or the existing system, but to enhance it with objective structural data.
Did the report show examples where this score might have changed things?
Yeah, they included a table, Table 4.4. It showed, for instance, a section of US 378 in Lexington County, where quite a few segments, over half the project length, fell into those tricky areas of interest, suggesting structural issues. The TSD score would flag that project, prompting a closer look.
It really sounds like a practical way to use this data. Do they look at what other states are doing? Is TSD common elsewhere?
They did survey 25 other state DOTs. It gives some good context.
What's the picture nationally?
Well, most states, 80% do collect some kind of structural data, but how they do it varies.
Still mostly the old FWD method.
Yeah, 60% use only FWD, about 20% use both FWD and TSD, and only about 4% use only TSD. So TSD is still gaining traction.
And are they actually using this structural data in their big picture planning?
That's where it gets interesting. Only 13% said they have actual guidelines for using structural data at the network level for planning across the whole state.
Only 13%.
But almost half, 48%, plan to develop those guidelines. So there's a big shift happening or planned.
What about using TSD specifically for picking individual projects like SCDOT is considering?
Even fewer have guidelines for that, just 4.3%. But again, lots are planning at about 39%.
So SCDOT exploring this is actually quite forward-thinking, putting them ahead of the curve in some ways.
It seems that way, yes. They're among the states actively figuring out how to integrate this newer technology.
Did anyone look at the cost effectiveness? Does collecting this data save money?
Not many yet. Only about 17% had actually studied the cost benefit, but another 22% or so are planning to. So the economic case is still being built in many places.
Okay, so given all this, the SCDOT findings, the national picture, what were the final recommendations from this study? What should SCDOT do next?
The main recommendation was pretty direct. SCDOT should really consider collecting TSD data routinely and using those TSD scores they developed in their project selection process.
Makes sense. What were the key benefits they hammered home?
They summarized it into three main advantages. One, identify those roads that look good but are structurally bad. Good PQI, poor SCI, so they get the right attention.
Avoid nasty surprises.
Two, inform investigations for roads that are iffy on top and bad underneath. Fair PQI, poor SCI. The TSD tells you where to look closer.
Target the field work better.
And three, avoid overspending on roads that look bad but are structurally sound. Poor PQI, good SCI. Use preservation instead of reconstruction where appropriate.
Save money, fix more roads overall.
That's the potential, yes.
Did they suggest how often SCDOT should collect TSD data? Every year.
They recommended SCDOT do a specific benefit cost analysis. That would help figure out the potential savings and determine the optimal frequency, how often they need to collect the data to make it worthwhile.
Right. Find the sweet spot.
Huh.
Okay, let's try and wrap this up. What are the big takeaways for our listener from this deep dive?
I think the main thing is that this TSD technology gives us a powerful new lens to see the real health of our roads, going beyond just the surface appearance measured by things like PQI.
It's like an X-ray for the pavement.
Kind of, yeah. And the study clearly shows that just looking at the surface can lead you to make, well, suboptimal decisions, maybe fixing the wrong thing or using the wrong, more expensive treatment.
And for you, the listener, driving on these roads, what's the potential benefit?
Ultimately, it could mean your tax dollars are used more effectively. Smarter decisions based on better data should lead to repairs that last longer, potentially delaying costly reconstruction.
So better roads, maybe smoother rides for longer, and better value for money.
That's the goal. More efficient maintenance, targeting the right problems with the right solutions.
Fascinating stuff.
Yeah.
And it makes you think, if this tech can reveal hidden issues in roads, what else could we apply this kind of thinking to?
Absolutely. This idea of using non-destructive testing, getting data about the inside without tearing things apart. Think about bridges, pipelines, building foundations.
Yeah, any critical infrastructure where failure is costly and inspection is hard.
Exactly. Data-driven approaches like this could really change how we manage and maintain all sorts of things we rely on every day. It's not just about asphalt.
A really thought-provoking point to end on. If you want to get into the real weeds on this, the original report is your next stop search for SPR 748-final-report.pdf. It's got all the details.
Definitely worth a look if you're interested.
Thanks for joining us on the deep dive. Until next time, keep asking questions and exploring the world around you.